Welcome to clickmyproject.com. Title of our product is two 122 GHz space lock loops in 65nm CMOS technology. Abstract of our product is two 122 GHz space lock loops have been developed based on the 65nm silicon CMOS technology, and their performances were compared in this process. For the first PLL, a voltage controlled oscillator with the frequency doubled. This is embedded into the oscillator core was employed into name as an PLL1, while the second PLL employs a push-pull voltage controlled oscillator. The output power of PLL1 and PLL2 were minus 8.6 and minus 21.9 dBm, near 122 GHz, obtained from DC power dissipation of 82.9 and 87.7 microwatt respectively. The respective locking range were measured by 121.9 to 122.2 and 122.7 to 122.9 GHz for PLL1 and PLL2. It consists of a VCO and 1 by 2 rejection lock frequency divider and 1 by 152 current mode logic. They are denoted as an CML based divider chain and a falling edge based frequency detector, and a charge pump and a second order loop filter. The main difference between the two PLLs is the voltage controlled oscillator structure employed. A DVO was adapted for the first PLL, and push-pull voltage control oscillator was used for the second PLL. Now we are going to discuss about the flow diagram of our product. In our product, we are using a different 4 modules to implement our product successfully. The 4 modules are falling edge based frequency detector, charge pump, voltage controlled oscillator, and current mode logic functions. The reference input signal will be directly applied into the phase frequency divider. This phase frequency divider output will be applied into the charge pump. In this charge pump, they will increase the charge of the frequency divider. The increased charge will be directly applied into the voltage controlled oscillator. The design of voltage controlled oscillators becomes increasingly challenging as the operation frequency increases. The main use of voltage controlled oscillator is obtain the two major approaches to obtain the high order harmonics in oscillators. This obtained harmonic output will be directly applied into the injection locked frequency divider. This injection lock loop frequency divider obtain the highly reasonable low power consumption. This include the Miller divider and the static dividers. In this, current mode logic will be run based on the conventional dual switch topology. This output of the conventional mode logic is a final output of our product. Now we are going to discuss about the running procedure of our product. Our product can be implemented by using a Tanner EDA 13.0 version tool. First, create a new schematic using this file menu. File to create a new design. Assign the design name on the desired path. After assign the design name, click OK to continue our product design. After creating the new file, to add the library files using this add option. To select the library file path, this documentation file. To select all files to open the all library files from this menu. After adding the library files, now you are visible the logic gates and some spice commands. Now start the schematic using the cell option to create a new view. To assign the cell name or not they are assigned as a default cell 0. Click OK to continue the design. In our product we are using two different cells. They are named as DE and push pull. Both are different voltage control oscillators for phase lock loopings. Now select the DE to set up the simulation files to start run our product. This is the library files of our path. We are using a generic 0.25 library file to select the library file. After selecting the library files, now assign the transient and Fourier analysis. Our stop time will be 600 nanoseconds. Maximum time setup is 1 nanoseconds. Print time setup is 0 nanoseconds. They are initially assigned the false and operation conditions. After assigning the setup simulation, click OK to complete the simulation. After complete the setup, now start run using this start simulation option. This is the output waveform of our DEPLL. Expand this waveform using this expand chart option. This is the output of our product. VQ bar and VQ is an output of our product, and then V clock is an input clock signal. V reference is a reference input signal. Up down will be denoted as an itself of our circuits. Now we are start simulate the second model of our push pull voltage controlled phase lock loop function. Now select the push pull and set up the setup simulation default for an first model. After selecting the library files, assign the transient and Fourier analysis. After set the setup simulation, click OK to start simulate these waveforms. This is an push pull voltage controlled oscillator output waveform. Expand this waveform. They are all the output of our product. V clock is an input clock signal. V reference is an input reference signal. VQ is an output signal. VQ bar is an inverse of output signal. This is an down operation. This up operation. This is a frequency divider function. Thank you for watching this video.